Hello everyone, in this video we're going to talk about paths in circuits. More specifically, this lecture will be breaking down into three different videos. In the first video, which is this video, we're going to go over some definitions related to walk, trail, circuits, path, and cycle. In the next video, we're going to talk about more special cases of path and circuits. It's called Eulerian paths and Eulerian circuits. And in the last video, we're going to talk about Hamiltonian path and Hamiltonian circuits. So why do we care about paths and circuits? In many cases, problems can be modeled with paths formed by traveling along edges of graphs. For instance, the problem of determining whether a message can be sent between two computers using intermediate link can be studied with a graph model. Problems in the real-world scenario, such as sufficiently planning routes for mail delivering, for garbage pickup, for diagnosing computer networks, can be solved using models that involve paths in graphs. So in this video, as I mentioned, I'm going to give you some concept related to walk, trail, path, and circuits and cycle. Now the issue is that there is variations of terminology concerning the concept that related to walk, trail, path, so on and so forth. For instance, some books, the term walk is used instead of a path. And the trail is used to denote a walk that has no repeated edge, and that terminology trail is replacing the term symbol path. And when the term path is used, often used for a trail with no repeated vertices and conflicting with definitions in one book compared to the other. Because of these variations in terminology, I just want to give you a warning that you will need to make sure which set of definitions are used in a particular book or article when you read about traversing edges of a graph. So what I'm going to do in this video is just give you kind of the characteristic of those terminologies instead of giving you definitions. But certainly when you do a problem, when you read a book related to this particular topic, you have to be careful with the definitions. So the terminologies that we're going to cover is a walk that can be opened, can be closed, a trail, a closed trail, which is a circuit, a path, and a closed path, which is a cycle. And again, I'm just going to give you the characteristic of each terminology and how when you look at the terminology with those characteristics, you can solve the problem. Alright, so I'm going to set up the table here. So in the first column, I have the name of the concepts I want to consider. And in the second column, I want to know if the graph is open. The third column, I want to know if the graph is closed. And I want to see if the graph has repeated vertex or repeated vertices. And in the last column, I want to know if the graph has repeated edge or repeated edges. Okay. So the first one is going to be an open walk. By the name, you know that the graph is opened, and for an open walk, you can have repeated vertex or repeated vertices, and you can have repeated edge or repeated edges. Now for the second terminology or the second type of graph, I have a closed walk. And this has to be closed. You can have repeated vertex or repeated vertices, and can have repeated edges. The third one is going to be called a trail, and the trail has to be open, and you can have repeated vertex or repeated vertices and no repeated edge. Now for a circuit, there's another name for this, it's called a closed trail. This has to be closed graph. You can have repeated vertex or vertices, and there should be no repeated edge. Now the next one is called a path. It's an open graph, no repeated vertex and no repeated edge. And the last one is a cycle, or there's another name for this, it's called a closed path. So it has to be a closed graph and no repeated vertex or vertices except at the endpoint. And no repeated edge. So these are the characteristics that allow you to identify if the graph that you're working with is an open walk, a closed walk, a trail, a circuit, a path, or a cycle. Alright, let's consider the following example. So I have this graph, And I'm going to write down some solutions related to an open walk, a closed walk, a trail, a circuit, a path, and a cycle. Okay, there should be multiple solutions to one problem. That means for an open walk, there should be multiple solutions. I'm just going to present to you one solution based on the characteristic that we see in the table. So for a walk, so I can start anywhere that I like. So let's start at V2. I'm going to go from V2 to V4 to V3 and then go back to V4 and then go to V1. So I go V2, go to V4, go to V3, now go back to V4 and then go to V1. So I can go from V2 to V4 and then V4 to V3 and V3 back to V4 and then from V4 to V1. I follow the characteristic that I see in the notes, and I see that this is an open walk, and I can have repeated vertex, which is here and here, and I can have the repeated edge, which is this edge right here. Now this one is an open walk. Now for a closed walk, so again I'm going to start at V2. So I have V2, I'm going to go to V4, I'm going to go to V3, into V4, and go to V1, and from V1 I'm going to go to V3, and from V3 I'm going to go back to V2. So again, I follow this particular path right here, so let me delete this. So I'm going from V2 to V4, V4 to V3, then V3 go back to V4, V4 to V1, V1 to V3, and V3 to V2. So this is a closed walk. Now for a trail, the characteristic is that this has to be an open graph. Repeated vertex or repeated vertices are allowed, but the repeated edge is not allowed. So let me delete this. I'm going to start at V2 again. So V2 I can go to V4, I'm going to go to V3, I'm going to go to V2 again, and then go to V6. So that's where I go. So here's for the trail, so V2 to V4, V4 to V3, V3 to V2, and V2 to V6. So here I have repeated vertex, but there's no repeated edge. Now for a circuit, which is a closed trail. Right, so the graph has to be closed. You can have repeated vertex or repeated vertices, but repeated edge is not allowed. So this is where I can go. So I start at V2 again. So V2 to V4, then go to V3, then you can go to V2, go to V6, and then you go to V3 to close the graph. So this is where I go. So V2 to V4, V4 to V3, V3 to V2, V2 to V6, and V6 to V3. So that's the circuit. Now for a path. So it's an open graph. Repeated vertex and repeated vertices are not allowed, and no repeated edge. So I can just go from V2 to V4 and to V1, and I have a path. So here I go from V2 to V4 and V4 from V to V1. And for a cycle means that it's a closed path, therefore the graph has to be closed. There's no repeated vertex or repeated vertices except at the end point. That means where you start and where you end should meet at one point, so that's allowed. However, there's no repeated edge. So for a cycle, you can go V2 to V4, V4 to V1, V1 to V3, and V3 you can go back to V2 to complete the cycle. So this is where you end. So V2 to V4, V4 to V1, V1 to V3, and V3 to V2. So that's an example where you have a graph, and from the graph you can identify an open walk, a closed walk, a trail, a circuit, a path, and a cycle. Now we're going to move on to another example, and we're going to do a similar thing. That is, given a graph, can you write down a solution for a walk, a trail, a path, so on and so forth. I didn't mention this in the last example, but sometimes a certain textbook and article also mentions about the edge that you use to follow the path or the trail or whatever. So in this case, I want to include that so that when you encounter something like that, you know what it means. So here, let's say here I have this to be edge E1, edge E2, E3, E4, E5, E6, E7, E8, E9, E10, E11, E12, and E13. It doesn't matter how you name it as long as you follow the characteristic of a walk, a trail, a path, and include the edge that you use. So for an open walk, again, the characteristic is that it has to be an open graph, the repeated vertex or repeated vertices are allowed, and repeated edges are allowed as well. So I can try with 1 to 2 to 3, go back to 2, and go to 4. For this particular walk, I use the edge E1, go to use E4, and then E4 again, and then E2. So this is a walk. So this is how I use it. So I go from 1 to 2, from 2 to 3, and then 3 go back to 2, and then from 2 to 4. Now for a close walk, I can do 1 to 2, very similar to the last case, to 3, then go back to 2, then go to 4. From 4 you go to 3, and from 3 you go back to 1. And the edges that I use going to be E1, E4, E4 again, E2, from 4 to 3 I use E5, and then E3 here. This is going to be my close walk. That is, I'm going from 1 to 2, from 2 to 3, then 3 go back to 2, 2 to 4, 4 to 3, and 3 to 1. That is 4 to 3, and 3 to 1. So that's I have a close walk. Now moving on to a trail. So this has to be an open graph. Repeated vertex and repeated vertices are allowed, but no repeated edge is allowed. So a trail can be, let's say 1, 2, go to 3, from 3 you go to 4, and from 4 you go to 2. So you have repeated vertex here, that is the vertex 2, and the edge that you use to follow this is going to be E1, E4, E5, and E2. And as you can see, there's no repeated edge in this for the trail. So what I did is I go from 1 to 2, from 2 to 3, from 3 to 4, and from 4 to 2. Now for a circuit or a closed trail, so this has to be a closed graph. I can go 1 to 2, 2 to 3, 3 to 6, 6 to 8, 8 go back to 3, and from 3 go back to 1. The edges that I use to follow this circuit is E1, E4, E7, E8, E9, and E3 to go back to 1. So I have a circuit, and this is how I go. So from 1 to 2, from 2 to 3, from 3 to 6, from 6 to 8, from 8 to 3, and then from 3 go back to 1. Now for a path. So it's an open graph, no repeated vertex and no repeated edge are allowed. So I can go from 1 to 2 to 4, and the edges that I use are so E1 and E2. Now this is how I go. So 1 to 2 and 2 to 4, and that's it. For a cycle, I can go from 1 to 2 to 4 to 3, and then I go back to 1. And the edges that I use is going to be E1, E2, E5, and E3. So it's a closed graph, no repeated vertex except at the endpoint, and no repeated edge. So this is how I go. I go from 1 to 2, 2 to 4, now 4 to 3, and from 3 I go back to 1, and I complete the cycle. And often you want to know what is the length of what you are doing, what is the length of an open walk, what is the length of a closed walk, what is the length of a trail, the length of a circuit, so on and so forth. And to determine the length of a graph, what you do is you count the number of edges it has, and you can count repeated edges as many times as they appear. For example, if you go back to an open walk here, you have E1, E4, E4, and E2. So there are 4 edges are used for this open walk, so the length of this walk is equal to 4. So this is an open walk of length 4. And going to be the same thing here. So E1, E4, E4, E2, E5, E3. So this is a close walk of length 6. And for this trail, this is of length 4. The circus is a length of 6. This is a path of length 2. And this is the cycle of length 4. And again, as I mentioned earlier, that there's multiple solutions to one type of graph. So an open walk can have multiple solutions to that. You can give a different open walk, and when you have a different open walk, the length of the walk can be different as well. In this case, an open walk. This is an open walk of length 4. You can have an open walk of length 5. You can have an open walk of length 3, so on and so forth. So again, in this video, I'm just going to give you a basic concept and terminologies of walk, trail, and path. And a warning I gave you earlier is that depends on the textbook and the material in an article that you read, the definitions of this type of walk, trail, and path can be slightly different, so you have to be careful. So that's why I didn't give you a definitions, but just the characteristic for different type of graphs, so that when you see the graph, you can identify if you are working with an open walk, a closed walk, a trail, a circuit, a path, or a cycle. Now in the next video, I'm going to talk about Eulerian path and Eulerian circuit.